All right, so we've done our, that sounds right in my eyes. It's a weird thing to say this time of year. Okay, oh shoot, bank shot. Okay. Yeah, so new subject. We are sitting right here on chemical reactions. So we're going to start on molar weights, Avogadro's number, and then balancing equations. And I'll do most of the balancing of the equation stuff next week when I get back. But we're going to get through at least some of the introductory stuff here. And you are going to want a calculator that is capable of exponents, right? Scientific notation, because we'll be using that for at least Avogadro's number as we go through this. All right. Yeah, then we'll have a quiz when we get back on nuclear chemistry, and we'll start in chemical reactions. We'll not start in, we'll finish chemical reactions on Tuesday. Okay? It's confusing to me too, when I like lecturing on something I'm doing on last week. And anyway, so, all right. So if you want to bring up the slide deck we're going to be using, it is, the next one's entitled Chapter 7, but yeah, go with that. We're going to be looking at chemical equations, a bit looking at using Avogadro's number, okay, which is at 6.02 times 10 to the 23rd. It's going to go to 3 significant figures for this class for the most part. Look at molar masses, balanced chemical equations, types of equations. We've touched on that already. And then the last thing I really want to look at is oxidation and reduction reactions. And those are pretty confusing, but I'm going to simplify them as much as I can. So at least you have an idea of what's going with reduction, oxidation, or redox reactions, because they're extremely important biologically. Okay, so first of all, let's start at the top here with a mole, an M-O-L-E, not the animal, the subterranean animal. It is a unit of measurement that describes the number of something, whatever it is. Just like a dozen is 12, right? A gross is 144. A rack, I don't know if that's a rack of beer back in my day was 24 beers. A half rack was 12. But anyway, you get the idea. It doesn't mean anything specifically, but is a description of the number of the same item. Okay, and we are going to be using it because we have such large quantities rather than writing out huge gargantuan numbers like 6.02, 333, and my arm would be tired from either typing or writing. We just use scientific notation, 6.02 times 10 to the 23rd, and then on your handy dandy calculator, 6.02 exponent 23, and there you've got Avogadro's number in nice scientific notation to help you do calculations with these huge numbers. Okay, let's see, Avogadro, yes, he was an Italian physicist. Why he picked this number, I have no idea. It is what it is. Why is a dozen 12? I don't know. Nobody knows. Okay, why is a gross of something 144? So, for instance, just to drive the point home, we can have a mole of an element, so 6.02 atoms of the element, so 1 mole of carbon is 6.02 times 10 to the 23rd atoms of carbon. Okay, and a mole of sodium, 6.02 atoms of sodium. Okay, so what where was that at? So you can have moles of atoms like aluminum and sulfur. And then when you start combining things using our covalent and ionic bonding, you get molecules. You're going to have a mole of water, which contains 2 moles of hydrogen, 1 mole of oxygen. Okay, in a mole of water, a mole of vitamin C has 6 moles of carbon, 8 moles of hydrogen, 6 moles of oxygen. Okay, but this entire molecule, there will be a 6.02 times 10 to the 23rd moles of vitamin C. Okay, so covalent bonding there. So hopefully that rings a bell. Then we have sodium chloride or salt, ionic bond, so you can have a mole of salt as well. Okay. So 1 mole is, just to really drive that point home, 6.02 times 10 to the 23rd particles. And here we go. For our dimensional analysis, that means we have a conversion that we can use 1 mole per 6.02 times 10 to the 23rd particles. Okay, so we're back to conversion factors, right? Conversion factors, dimensional analysis. This is all about really understanding that idea and how we can use it, okay, in beginning chemistry. Okay, so let's dive right in and start doing some calculations. So any of you who are math averse, if you're not following along, unmute yourself or shoot a comment in. I'll leave that open. Shoot a comment in. And make sure that you understand before I move forward, because I'm building the base of the building, and then we're going to add more stuff. And hopefully each step isn't more complicated than the step before, but by the end, you should be have this wonderful building that you built with mathematics. That was kind of poetic. I'm proud of that. Okay, so let's look at, and yep, here goes my pad. We have our first problem. We have an Avogadro's number. How many carbon dioxide molecules are there in 0.5 moles of carbon dioxide? Okay. So we are given 0.50 moles of CO2. Okay, that's what we're given. I'm going to shrink that down just a skosh. Got a little more room to work with. Okay. And then we also know from my introduction that for every 1 mole of CO2, okay, we have 6.02 times 10 to the 23rd atoms. Okay. Now let's make sure that we set it up correctly, like we've been doing. We have moles crossing out moles, right? And we're left with the number of particles. And if you multiply 0.5 times 6.02 exponent to the 23rd, that will give us 3.01 times 10 to the 23rd. Okay, yeah. Particles. Okay. And let's see if I can get all fancy here. Yeah, look at that nice straight line. Okay, then running that down, we set this up just exactly the same way I did. 0.5 moles over a mole of CO2. Yep, molecules of CO2 at 3.01 times 10 to the 23rd. So far so good? Okay, I'm going to assume a thumbs up before I move on. Okay, so I will do, let's see, I think I have another example. Yeah, so I will work through another one. Okay, what is the number of atoms in 2.0 moles of aluminum? Now, let's see if I can even get fancier. No. Ooh. Okay, look at that. Okay, what is the number of atoms in 2 moles of aluminum? Okay, so we are given, all right, 2.0 moles of aluminum. I'll set up our conversion. Okay, so for every 1 mole of aluminum, there are, again, 6.02 times 10 to the 23rd atoms of aluminum. Okay, now let's double check our math. That crosses out. That crosses out. We're left with a number of moles of aluminum. Take 2 times 6.02 exponent to the 23rd. And we have only 2 significant figures right here. So 1.2 times 10 to the 24th. Let's see, atoms of aluminum. Okay. And let's go up here and take a peek if that corresponds to anything, and look, it is right there. Okay. Everyone okay with that? More or less? An excellent question. Because does anyone want to help Daniel out with that? Okay, I'll do it then. So scientific notation is what? It has to be a number between 1 and 9.999, right? Okay, so this number, we could also write it as 12 times 10 to the 23rd, right? But that's not scientific notation because 12 is greater than 10, right? So what we have to do, we have to move that decimal back to there. Okay. Okay. So we have to multiply the whole thing by 10 to move that decimal. And then that moves that 23 to a 24. Okay. Make sense? Okay. Excellent. I'm sure someone else had the same question. So, all right. So now let's see. I think your times size, 6.02 times 10 to the 23rd, 1.2 times 10 to the 24th. The answer is C. Yes. Did I lose somebody? Okay. All right. So I would like you to answer this question. What is the number of moles of sulfur, okay, in 1.8 times 10 to the 24th atoms of sulfur? Okay. So I'm going to say this is going to be similar, but a little different. I'm hoping that you'll be able to reason your way to doing this. Oh, sticks. Okay. Still learning my way around this board. Okay. I'll give you a few minutes to reason your way through this. But it does, well, I mean, a little hint, it does involve some conversion, a little dimensional analysis. And I'll tell you what, once you get an answer, put A, B, or C over as a message. Okay, Maria. All right. Oh, yeah, Natalie. So, yeah, so just write down here, this little thing right down there. Just click. Oh, poof. Yeah, you might be out of luck. I don't know if you can comment from your phone. I've never been on one of these on a phone. I've only done like some of the other ones. But there's probably a way to do it. Okay, so let's work through it. Looks like we've got a nice start from folks. So once again, okay, we are given 1.8 times 10 to the 24th atoms, okay, of sulfur. I said we're going to need that conversion. And we also know that for every 1 mole of sulfur, we have 6.02 times 10 to the 23rd atoms of sulfur. Okay. Cross out those two units. We're left with our number of moles. Okay. 1.8 exponent is 24 divided by 6.02. Exponent is 23. Okay. And 2.99 rounding up to exactly so 3.0, two significant figures, moles of sulfur. Here we go. Yes, Natalie. Or was it? By definition, a mole of something, a mole of people, a mole of atoms, a mole of is, yeah, yeah. Okay, we are cooking with gas now. All right. Um, and set that up. The answer was B. Excellent. All right. And I'll also send you guys a copy of my worksheet I've been working on as well. It tends to be a little more um, simplified, compacted. Okay, so we've looked at individual atoms. Now let's look at some molecules. We have some aspirin, acetyl salicylic acid. Has 9 carbons, 8 hydrogens, and 4 oxygens in each molecule of aspirin. Okay, we're going to start with that little factoid. So within each molecule of, or excuse me, each mole of aspirin, we're going to have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen in each 1 mole of aspirin. Okay? Yeah, sort of like if you had a dozen cars out there, there would be how many tires? Okay, 4 per car, so 48 tires. Same kind of thing. Okay? I don't know if that helped or not. All right, so this gives us a whole series of possible conversions, a number of moles of carbon in a mole of aspirin, mole of hydrogen in a mole of aspirin, and the moles of oxygen in a mole of aspirin, 9, 8, and 4, respectively. Okay. So let's look at some problems using this idea. Okay. So how many atoms of oxygen are in 0.150 moles of aspirin? Okay, so I'll do my little snip and paste. Okay, how many moles of oxygen are in 0.15 moles of aspirin, C9H8 0.04. Okay. So let's quickly set this up. So we're given 0.150 mole, and I'm just going to abbreviate it ASA, acetylsalicylic acid. Okay. Okay. For now, let's think through this. For every 1 mole of aspirin, okay, we have how many moles of oxygen? 4. Exactly. 4 moles of oxygen. Okay? But it's not asking how many moles. It's asking us, of course, how many atoms there are. So we need to keep going. Okay? For every 1 mole of oxygen, we have, of course, 6.02 times 10 to the 23rd atoms of oxygen, right? So let's make sure we set this up correctly. We have moles of aspirin, okay, moles of aspirin, moles of oxygen, and we're left with the atoms of oxygen. So all we need to do is pull out our calculator and find out what that number is. So 0.150 times 4 times 6.02 to the 23rd. And let's see, 150, we have 3 significant figures it looks like we started with. Okay, so 3.61 times 10 to the 23rd atoms. Always put your units of oxygen. Okay, and I will boom. Okay, so let's make sure that we set this up correctly. 0.150, 4 moles of oxygen per 1 mole of aspirin, and per mole of oxygen. Yeah, so 3.61 times 10 to the 23rd. Okay, awesome. Actually, we're making really good time. Okay. So that's the first thing I wanted to familiarize, idea I wanted to familiarize you with. The next thing is using the concept of molar mass. So mass, we're talking about weight. Sort of. We'll count mass as weight. Okay, so on your periodic table, you have, remember those numbers below the atomic symbol? Okay, to 2 significant figures usually. Now we're going to use that, okay? And what that's telling you, for in this case, for every 1 mole of sodium, you have 22.99 grams of mass, okay, on the surface of planet Earth. So I just want to kind of put that out there, and then I'm not going to say that again. But there are 22.99 grams, okay, right here, of sodium in 1 mole. In 1 mole of sodium, there are 22.99 grams, okay? So using that fact, we can do some kind of interesting things, actually. Okay, so for carbon, each mole of carbon, 12.01 grams. For each mole of lithium, 6.94 grams. Okay, so we have a whole nother set of conversion factors built into our periodic table to help us do calculations. Right, so yeah, just saying is all you do. Okay, you weigh out 107.9 grams of silver, you're going to have a mole of silver, etc., etc. So yeah, like that. So what? Great. Well, I'll tell you what. We're going to do more math. Okay. So we're going to calculate. So molar mass of elements, easy. Look it up, write it down, move on with your life. However, an awful lot of things come as molecules, which are a combination of elements. So what we're going to do is figure out how much a molar mass is of various molecules. Okay, so here we have lithium carbonate. That's a ionic bond between a metal and a polyatomic anion, right? So hopefully that made sense. If not, that's fine. Just let it kind of wash over you. So lithium carbonate here, okay? What is the molar mass of lithium carbonate? So the first thing that we need to ascertain is we go to our periodic table, and for each of the elements that are in lithium carbonate, we are going to write down what the molar mass is. Step one. Okay? Just add them up? No, not quite. So what the next thing we need to do, next order of business, is again we have lithium carbonate. Was it CO3? Yeah, I went to CO3. Okay. Lithium carbonate. There we go. Oh. The molar mass. What does 1 mole of lithium carbonate weigh, essentially? Is what they're asking. All right. So let's take the first thing. We have lithium. Let's add it up. Okay, we have in each mole of lithium, we have 2 moles. Or in each mole of lithium carbonate, we have 2 moles. Okay, times the molar mass, which is 6.941 grams per mole. Okay, let's see. 1 mole of lithium times 2. Okay, and then we have carbon. So 1 mole of carbon. Okay, 1 mole times 12.01 grams per mole. Okay, and the last atom that we have, our last element we have in that, is for each 1 mole of oxygen in lithium carbonate, there are 3, right? 3. And each one of those weighs 16 per mole. Now, again, let's see. So we're doing this in triplicate. So 1 mole, 1 mole. Okay, 1 mole, 1 mole, 1 mole, 1 mole. Okay, of lithium, carbon, and oxygen. Now we just need to do the math. So 2 times 6.941, what's 13.88? Yeah. 13.88 grams. Okay. So 1 times 12.01, I don't need a calculator for that. 1 grams there. And 3 times 16 is 48.00 grams of, let's see, we have lithium, we have carbon, and we have oxygen, right? So the last thing we do, we got to add all of those up. 13 plus 12 plus 48, 13.88 plus 12.01 plus 48 gives us 73.89. 9 grams, 9 grams, what? Grams per mole of lithium carbonate. Okay, so that's exactly that. 2 moles of lithium, 1 mole of carbon, 3 moles of oxygen per mole of lithium carbonate. Found out how many grams there were in each mole of lithium carbonate for each of those elements, added those all up, and got our answer of 73.89 grams is the molar mass of lithium carbonate. Okay, questions about that? Does that make sense to everybody? Okay. So let's delve in to this. So I would like you all to calculate the molar mass of, what is that, carbon, well, I'm not really seeing what that is, but of C2H6O, molar mass of that, using a combination of your, and yeah, feel free to use your periodic table to get you kind of going. In fact, we have most of this already from our previous example, but okay. And then when you have your answer, type it in just like you did. I don't have A, B, or C on this one, but two, yeah, I'm assuming 4 significant figures. Okay. Nice. Maria and Ken. Thank you, Willow. Slight disagreement here. Okay. Okay, good, Don Tirius. There we go. Nice. Okay, so let's go ahead. Yeah, great. And take a look here. So we know the molar mass of carbon is, from up above, 12.01. I'll just kind of do this little 12.01 grams per mole. Okay, molar mass of hydrogen is what, 1.001? Is that what they have? I think. Yeah. 1.008. Okay, thank you. I misremembered. Hey, it ain't easy being old. Yeah. Okay, thank you. And then oxygen came in at an even 16.00. grams per mole. And then we have, for each mole of that molecule, we have 2 carbons. I'm kind of setting this up, 6 hydrogens, and 1 oxygen. Okay. So 24.02 grams per mole. Okay. 6.0048. Yeah. 6.048 grams per mole, okay, of carbon, hydrogen. And then just easy peasy, 1 mole of oxygen will give us 16 grams per mole. Add these up, plus 6.048 plus 16.00. Okay, and I came in with 46.0, and then we have to round to the 4th significant figure, grams per mole, which is the molar mass. Yes, sir. Yeah. So so let's look at significant figures. We should go to 4 significant figures. Yeah. Because we've got 4 significant figures, 4 significant figures, and 4 significant figures. Yeah. 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 So, yeah. Good question, though. Yeah, significant figures can definitely throw folks off. So let's see how we all did. So we have 12, R1, we're 16. We multiplied our 2, R6, and R1. We got 24.02. See, now these stinkers, they used a rounded, only 3 significant figures on their hydrogen. So we didn't use that. So I think our answer is going to be more correct. We got 46.08. We came up with 46.0. I think that's a mistake. I think 46.07 is the more accurate answer. But okay. But 46.08, 46.07. So if you got either one of those, you know what you're doing. Okay. 46.5. Huh. Uh-huh. So what did you use for the molar mass for hydrogen? And 1.008 times 6, I think you might have left a 0 out. Yeah, I think you might have left a 0 out, a sandwich 0 out. Yeah, yeah. So I think you probably put like 1.01 instead of 1.001 is my, or 1.08 instead of 1.008. That's my guess. I'd have to see it actually doing it, but I think that's what happened. Now, if you add up, yeah, yeah, yeah. Sometimes you do everything right and you punch it in the calculator wrong, and so you got to go back and figure out where things went awry. Okay, so last thing is just a concept. So molar quantities change, right? Here we have molar quantity of sulfur right there, iron, low, so high density, okay, same mass. All of these have the same number of particles in them. here's a mole of sodium chloride. Well, I mean, excuse me, a molar quantity of sodium chloride. Potassium chromate. Yep. And C12, I don't know what that is. Probably sugar. Yeah, one of the sugars, right? So that's the idea. The idea is the number of particles is what's important. Okay, keep your mind on that. But these all have a molar mass of 1. Okay, I think I'm going to leave it there. How deep oh, yeah, we got a nice. Okay, so I will, I'll review this at the beginning of class, and then we'll start in with the rest of our molar mass calculations, and we'll start doing some balancing. So, and if you got the balancing in nuclear chemistry, I don't think you're going to have that much trouble balancing chemical equations as well. So, same idea. All right, so that is all the speaking I'm going to do today. Let me stop recording.